Now that we've solved for I1 in this example, we need to go back and solve for I2 and I1, and then find the voltage drops across all three resistors. Remember earlier, we solved for I1 already. We can just use the same equation, that I1 is equal to EMF2 minus I3 times R plus R3, little r plus R3, all of that divided by R1. And so that means that I1 is going to equal EMF2, which was 45 volts, minus I3, which we just found to be 1.725 amps, times 1 ohm plus R3, which we said was 40 ohms. 40 ohms. That would be this resistor right here. All that divided by R1, which is this resistor here, 30 ohms. When you do that calculation, you find that I1 is equal to a negative 0.8581 amps. Notice the negative here. What does that negative mean? It means that when we first decided our directions for currents, that we actually got I1 incorrect. So instead of the current looking like this, I1 is really looking like this, excuse me. That's all that it means, is that our direction of I1 was incorrect. That's okay. Now that we saw that our magnitude for I1 was negative, we can just say, okay, go the other direction. No issue at all. All right, so we have I3, we have I1. Now we can go back and get I2. Remember this big long equation that we solved for I2 earlier? Well, we could go through and do that, or there's another equation we could use. We could just use the junction rule equation. Now that we have I1 and I3, we could just use this. So now I2 is going to equal I3 minus I1. I3 we found was 1.725 amps, and I1 we calculated as a negative 0.8581 amps. I have to keep the negative in because when I first set up all of these equations, I had assumed a direction for I1, so I have to maintain that direction for the rest of the problem, so that negative needs to stay in there. When you add that up, you end up with I2 equaling 2.5831 amps. Okay, so now that we've solved for all the currents, let me finish writing these up in here. So I2 is, whoop, come on, there we go. I2 we just found was 2.5831. And I3 was, I don't know why I wrote it this way. Whoops. This was I3. And this should be I1. It's going to be negative 0.8581 amps. And now we need to find the voltage drop across each resistor. Again, there's R2, R3, and R1. So the voltage drop across resistor 1 is just going to be I1, R1. Now, the direction of the current doesn't matter here. The current goes through the resistor either way. So the current here would be 0.8581 amps times the resistance, 30 ohms, which means that there was a total voltage drop of 25.7 volts across R1. The voltage drop across R2 would be I2R2. We found that I2 was 2.5831 amps times R2, which is 20 ohms, gives us a total voltage drop of 51.7 volts. And then finally, V3 would be I3R3, the current going through the resistor times the resistance itself, 1.725 amps times R3, which is 40 ohms, gives us a total voltage drop of 69 volts. So here you are, you found your currents as well as your voltage drops across each resistor, all using Kirchhoff's rules. Is it a lot? It can be quite complicated like you saw here. I am generally a fan of not putting in numbers until the very end. That can get really messy here with Kirchhoff's rules. And so, yes, go ahead and plug in your numbers early on. You could have even plugged in your numbers way back here if you wanted to and simplified these equations a little bit. So there are lots of ways you can do this. Hopefully this video helped show you a little bit more about how to use Kirchhoff's rules. Please send me any questions should you have any.